So today I'll talk about combinatorial discrepancy. It's a very beautiful area within combinatorics, and it has a very rich and broad history. So I'll just cover a very tiny fragment of it, but hopefully you'll be intrigued enough to pursue it further later on. And throughout this talk, at any point, if you have any questions, just stop me and ask anything you have on your mind. So let me start by talking about combinatorial discrepancy. So what is it? So the main object of study here are set systems. So you have a universe, usually we'll denote it as the set of n elements, and you have a collection of sets, S1 up till Sm, where each Si is a subset of the universe. Okay. And for example, you can visualize this by drawing a matrix. So you have 1 through n here. These are the columns corresponding to the elements of the universe, and the sets you can denote by rows. So you have S1, S2 up till Sm, and you write down the indicator vector for the set I. For example, this could be just something like this, 0, 0, 1, 1, and so on. So you put a 1 whenever the element belongs to the set, and 0 if not. And what we are mainly interested here is to color the elements of the universe with 2 colors, so that each element, each set from your collection of sets is as balanced as possible. So what do I mean by that? We want a coloring vector which will be chi throughout the talk. So this is an element of 1 minus 1 through the n. Think of this as red or blue. Red is 1, blue is minus 1. And we want each set to be as balanced as possible. In particular, the imbalance of any set is exactly the sum of the colors of elements within that set. So this is the imbalance of the set Sj. And what we are interested in is finding colorings which minimize the maximum imbalance. So we want to maximize this over all sets Sj in your collection, and we want to minimize this over all possible colorings. Okay. And this for us is the discrepancy of the set system. Okay. And this is the main object of study for this talk. Okay. So if you want to think about discrepancy in more colloquial terms, let's say, so you can think of, let's say you have some kind of voting mechanism. 1 means doing well, minus 1 means not doing so well, and you have a collection of people 1 through n who you want to rate as doing well or not doing well. And you have some subsets of groups, like let's say you have lawyers, doctors, engineers, scientists, and so on. And you want to label people doing well or not, but you want each collection of people to not be dominant over the others. Okay, it's some kind of egalitarian mechanism. And as I said, this has a very rich history and many applications, which I'll talk about in a few more minutes. And the history starts from the early work in early 20th century, really, where number theorists studied this problem, or a close relation of this problem. So early 20th century by number theorists. So they studied this topic under the name irregularities of distributions. Okay. And since then it's taken off, especially in the past few decades because of its relation to computer science, as we'll see. And so here's today's outline. So I want to cover three main results in this talk, in this tutorial. The first is the Beck-Fiala theorem. From 81. And this will lead to one of the central open questions in the area. And second one is relation between, well, let me write it this way. And the second will actually be an application to computer science problems. And this will be in the form of rounding algorithms through discrepancy theory. Okay? And this is a very beautiful result of Lowa, Spencer, and where is the Combi from 86. And the third and final result will be a new proof, or relatively recent new proof of the partial coloring lemma. And as we'll see, partial coloring lemma is one of the central techniques that's used in bounding discrepancy, and it was introduced by Beck in 1980. And we will give a new proof of it, which also turns out to be simpler and constructive. And finally, I'll finish with some open problems, which is probably the most important part of the talk, because I hope some of you will start working on them. Okay. All right, so let's get started. And before getting into these things, let me just throw some buzzwords at you about the applications of this area. I don't want to go into too many details here, but there are two very nice books on this topic by Bernard Chazelle and Yuri Matusek, and you can find most of the applications there. But today I want to focus on this. But some of the main applications are to computational geometry, where discrepancy theory helps in finding good data structures, proving lower bounds, and so on, to communication complexity, where once again discrepancy theory helps in additional communication complexity lower bounds, and finally to, well, not finally, but to pseudo randomness. And in the design of pseudorandom generators for various classes, discrepancy theory comes up naturally, and also to complexity theory. And as we will see in application 2, to algorithm design. So I won't go into any of these applications here, but we'll see one example of the application to algorithm design later in the talk. Okay. And I'm only focusing on computer science applications here, but there are also connections with various areas in mathematics, to Fourier analysis, and other nice questions in combinatorics. Okay. And along the way, we'll see two of the broad techniques that people use in combinatorics. One is the linear algebraic method, and the other is the probabilistic method. So both of these are some fundamental techniques and methods. So we'll see examples of this. So even if you're not really interested in discrepancy theory, you should really care about these methods because they're beautiful, very simple, and extremely powerful. Okay. All right. So let's begin with. So this is what I want to say about the broad outline of this tutorial, but let's now dig into the details. Okay. And okay. Let me just state a few examples of discrepancy bounds. Okay. So given any set system, something like this, we want to estimate its discrepancy. And one of the first questions that was studied here was the set system corresponding to arithmetic progressions. And so this is arithmetic progressions. So here your universe is of size n, 1 through n, and the set system comprises of all possible arithmetic progressions. For example, you'll have something like 1, 3, 5, 7, and so on, and 1, 5, 9, 13, and so on, and so forth. Okay. So you have all possible arithmetic progressions here. So just as a quick reminder, how many sets will we see here, roughly speaking? We should see about n squared sets, right? Because an arithmetic progression is defined by two parameters, the starting point and the difference of two consecutive elements. So there are roughly theta of n squared elements in the collection. Okay. So this was studied.
You're only looking at progressions to go all the way up to n?
Yeah. So this was studied by Roth in 1964, who showed that the discrepancy of the set system is at least n to the 1/4. Is at least a constant times n to the 1/4. And this is a seminal result because it introduced various techniques that we still use to this day, which are simple in hindsight, but at the time they were very novel. And many people thought that actually there was an upper bound of root n, which was known at the time of Roth's work. And many people, in fact, I believe, were under the impression that the upper bound is the true answer. Okay, but that was shot to bits by this by the breakthrough work of Beck in 80, where he also introduced the partial coloring method, which we'll see later on. And he showed that discrepancy is log n. Okay. And this is very surprising to me because there are n squared sets, but the discrepancy is only n to the 1/4. Okay. And finally, after a few more years, Spencer and Matusek, mid-90s, close the gap by showing this is actually off to the 1/4. Okay. So they settled the problem, which started from the work of Roth from nearly 30 years back. Okay. And we'll see the partial coloring method, and it's a nice, I mean, it's more than a small exercise, but given the partial coloring lemma that we'll see later on, it's not too hard to deduce this bond for discrepancy. Okay. Right. And there are many other examples, but I don't want to go too much into them. If you are interested, just talk to me later. Okay. So let me now talk about the first result here, the Beck-Fiala theorem, and that uses the linear algebra method, which I said is by itself powerful, and its specific application in the Beck-Fiala proof that we'll see also has been used for many other problems, especially in analysis. And I won't be able to go into those details, but I'll point you to a nice survey paper. Okay, so now we're going to look at Beck-Fiala theorem, and it's a result about the bonding discrepancy of set systems of bounded degree. So what do I mean by that? So you have a universe n as before, and you also have a parameter t. Okay. And you have a collection of sets of sets S1 up till Sm. Okay. And the assumption is that each element in the universe appears in at most t sets. Okay. So the assumption is that each element appears in t sets in less than or equal to t sets. So if you think of the matrix representation, you have the sets here, and you have the elements of the universe on the columns, and the assumption is that each column here has at most t non-zeros. Okay. Okay. And so we want to bound the discrepancy of such. That's the only goal. That's the only assumption we are going to work with. Okay. And the main theorem of Beck and Fiala from 81 is that the discrepancy of any such set system with degree at most t is bounded by 2 times t minus 1. Okay. This is a bound from nearly 30 years ago. It hasn't been improved much, except that it's been reduced to 2t minus 3, I think. But not much. Okay. So the most interesting thing to note here is that the discrepancy bound does not depend on the size of the universe. It's independent of n. It only depends on the degree t. Okay. So for example, so why is that surprising? To understand why it is surprising, let's look at what happens to the discrepancy if you take a random coloring. Okay. Discrepancy so let's say you have a set system like before, and you take a random coloring chi, just a random plus or minus 1 vector, and you color the elements using that vector. So what should the discrepancy of the set system be? Okay. So for example, if I take a single set S, okay, then chi is uniformly random from 1 minus 1 to the n. Okay. And I sum up the entries in the set I. So what should the bound on this be? What will the sum be approximately most of the time? Well, the expectation of the sum is 0, right? But I'm putting an absolute value. So what's the expectation of the absolute value of the sum? It's no longer 0 because it's positive all the time, right? So question is, what is the expectation of, well, let's even simplify and say I equals 1 through n. So if I take n plus or minus 1 signs, what should the expectation be? Who said n? N is always an upper bound because each one is at most 1, but we should expect some cancellations, right? And come on, it's okay. I mean, just take some guesses. It's fine. Yeah. It's always even, so it has to be an even number. That's a good point. But we are interested in much cruder bounds. I want an asymptotic upper bound. Okay. And the real answer is that this is going to be theta of square root of n. Okay. So even though you're summing n things here, each one has 1 or minus 1, you should expect a lot of cancellations. And in particular, you're only going to be root n far away from 0. Okay. And you will actually be root n far away with high probability. Okay. So one simple way to see this is to calculate the variance of this sum, which will actually be n, and then use Cauchy-Schwarz. So if you take n signs, then it's roughly theta of square root of n. And if you take size of s things, this should basically be the expectation of this is roughly theta of square root of size of s. Okay, that's for a single set. But now remember that in our collection there are many, many different sets. Okay. So what happens then? How many of you have seen Chernoff bounds before? Okay, so that's not too many people. So let me quickly revise them, because they'll motivate many of the things we'll see, and it's also something that we'll use later on. Okay. So Chernoff bounds, and this is again one of the mainstays in the probabilistic method, analysis of randomized algorithms in computer science and everywhere. And in its simplest form, which is all we'll need today, it says the following. There are many, many strong generalizations, but we'll look at the simplest form. Let chi be random 1 minus 1 to the n. Okay. So let me put m here. If I take a random plus or minus 1 vector of length k, so by this statement here, the expectation of this sum is basically about square root of k. Okay. But I also want to say something more. I want to say something more, that not only is the expectation about square root of k, but the sum is actually close to square root of k with high probability. Most of the time it's about square root of k. So I want to bound the probability that the sum is much more than square root of k. Okay. So this is chi is uniformly random, and square root of k here is the standard deviation. Okay. So what I want to bound is the probability that the sum is t standard deviations away. Okay. And how many of you have seen Markov's inequality before? Okay, so that's a lot more people. So what happens if I apply Markov's inequality to this sum? I know that the expectation is about root of k, is theta of root of k, and if I use Markov's inequality, I get that the probability is at most it's 1 over t. Okay, this is by Markov's inequality. So this is fine, but actually something much stronger is true. Okay. So Chernoff's bound says that this is at most 2 times e to the minus t squared by 4, let's say. So the bound, the probability, not only is it at most 1 over t, but it's actually much, much smaller. It decreases exponentially in the square of the number of standard deviations you are away from. Okay, it's at most e to the minus t squared by some constant. And if you're familiar with the Gaussian distribution, the t squared here is very related to the t squared you see in the definition of the Gaussian distribution, standard Gaussian distribution. Okay. So let's keep this in mind and apply it to bound the discrepancy of random coloring. Okay. So now I have a set system S, S1 up till Sm, okay, and these are all elements of from a universe of size n, and I want to bound the discrepancy under a random coloring. So let's say chi is random, 1 minus 1 to the n, okay. So if I apply this claim to the first set, then I get probability that okay. So I just use the Chernoff bound to bound the probability that your t standard deviations away for this sum. Okay, and I can write down similar inequalities for all of the m sets. Okay. Okay. This looks very good to us, but the problem is that the coloring chi satisfies each constraint, but we don't know what happens across the different sets. For example, a coloring chi might satisfy the first constraint here, have small discrepancy for the first set S1, but not satisfy the second probability inequality. Okay. So let me simplify this bound, and since the size of each set is at most n, okay, that's a universal bound because the universe is of size n, I can replace this here with square root of n, okay, and so forth. So now we'll use something called the union bound. And how many of you have seen the union bound before? Okay, so it's still fewer than expected. So let me just briefly describe it.
I bet the people will recognize it, they just don't call it the union bound.
Okay, so let me just state it then. So I want to take a random coloring, and let's call an event bad, okay, the set S bad, if the discrepancy of the set under that coloring is more than t times square root of n, okay, which is bad for us. We want small discrepancy, and that's not happening. So there exists I in let's say J in M such that okay, this is the probability that at least one of these inequalities is violated. Okay. So at least one of the sets has discrepancy more than t times square root of n. The union bound says that if you have m events like this, then the probability of the union happening is at most sum of the individual probabilities. Okay. So this is at most 2 times m times e to the minus t squared by 4. Okay. So I just summed up all of these probabilities here. Now if I set t to be some O of square root of log m, okay, so if I choose such a big T, then what happens to this bound? This is going to be less than 1, okay, because square root of log m is log m, and e to the minus log m is going to be 1 over m if I choose a big enough constant here. Okay, so this probability is less than 1, and if the probability is less than 1, it implies there exists at least one coloring where none of these events happen. So this implies there exists chi belonging to 1 minus 1 to the n such that discrepancy of the set system under the coloring chi is less than, so t was O of square root log m, and we have a square root n bound here, so we get O of square root n times square root log n. Okay. So this is a trivial, not trivial, but a simple bound that you have for all set systems, depending only on the size of the set system. Okay. And we'll come back to this later on, whether or not this is tight, if we can improve it in the second half of the tutorial. All right. So that was a bit of segue to motivate why the bond in the Backfill theorem is so interesting. Well, if you take a random coloring, you get a bond of square root of n, which depends on n, and you cannot avoid it. For example, even if you're so the only constraint on the set system here is that each column has at most t elements. There is no bound on the number of elements in each row. So for example, S1 could be all the elements. And then I can have, let's say 0, 1, 1, 1. Okay. So if your set system looked like this, the first set was everything, and everything else was a singleton. Okay. Then if you apply random coloring, you get a discrepancy of theta of square root of n. Whereas Backfill theorem says that the discrepancy should be 1, should be at most 1, right, because t is 2. Right. So you need to somehow introduce a lot of cancellations. Okay. All right. So okay, so let's try and prove this statement now. And so as I said, you need to take special care of sets which are too large. Right? You need to introduce cancellations for them. You can't just take arbitrary colorings. So the way we will quantify such sets is by looking at the sizes, how big they are, okay? Looking at their sizes. So the proof will be algorithmic. So we will give an algorithm which will actually find the coloring and hence prove that there exists such a coloring. Okay, so it's a constructive proof in that sense. So what's the proof? So so it's called the method of, well, this is somewhat of a informal term really, it's not a formal term, of floating variables. Okay, and so there's a very nice survey by Imre Barani called on the power of linear dependencies. So this survey contains other examples of this method applied to various problems. So if you're interested, you should look up the survey. It's a very nice survey, nice and short survey. So the proof will go in phases. So in phase 0, this is what's going to happen. So phase 0. So you have a set F. Okay. So we want a 1 minus 1 coloring, right? We want discrepancy vector chi to be 1 or minus 1. So let's first relax the problem. It seems hard to come up with a 1 minus 1 coloring. So let's start with something simpler. Let's start with vector x in minus 1, 1, the interval. Okay. So now each xi is a real number, it's not just 1 or minus 1, but it can take any value between minus 1 and 1, okay, such that discrepancy of x is small. Okay, and we will carefully modify such a vector x to get a vector which is 1 minus 1 to the n. Okay, so we'll slowly make it more and more integral. Okay, and this is what we'll mean by rounding. Okay, and can you tell me one simple vector x which has very, very small discrepancy? Right. So phase 0 will start with x equals 0. Okay, so this is our initial guess, and we're going to slowly change this vector to get 1 minus 1 things. And the way we'll do this is to set each coordinate to 1 or minus 1, and that's why it's called floating variables, because in some sense you have n floating variables here, x1, x2 up to xn. Okay, so initially all of them are floating, we don't know their values, but in subsequent rounds we'll fix some of them be 1 or minus 1 and freeze them, and the others will be floating still. Okay, so we have a set f which is floating variables, and this is n to begin with. This is a set of all 1 through n at the beginning. Okay, and we need to now change the set of floating variables. Okay, so decrease its size by fixing one of these elements to be 1 or minus 1. Okay. So how do we do that? Well, so you want to fix the variables so as to not hurt the discrepancy too much, and here we introduce something called dangerous sets. Okay, so Si is dangerous, let me call it Sj, if, so you have your set system S1 through Sn, and we'll say a specific set in this collection is dangerous if is greater than t. Okay, so you have a set of floating variables f that will change throughout the execution of the algorithm, so it will keep decreasing, and a set S is dangerous if the size of its intersection with the floating variables is more than t. Okay, so let me draw a figure. Can everyone see red here? Okay. So you have 1 through n, and you have sets S1 up till Sm. Okay, and so initially all of this is the floating variables. Okay, and a set is dangerous if the size of its intersection with floating variables is greater than t. So if you look at it in terms of this matrix, what does it say? Right? So it says that a set is dangerous if I only look at the columns which are colored green here, that is set of floating variables, the sum of the entries in that row is more than t. Right, because that counts the size of the intersection with the set of floating variables. Okay, so let's say, for example, if the set was 1, 1, 1 up till 1, then S1 would be dangerous, right? Because the sum of everything is n, and n is much bigger than t, let's say. So this it's dangerous. And we'll have some other sets which are dangerous and some are not. Okay. So the first claim I want to make at phase 0 is the following. And this will be very important, and this we will maintain as an invariant throughout the proof or execution of the algorithm. So what's the claim? The claim is that number of dangerous sets is less than the number of floating variables. Okay. So the number of dangerous sets is less than the number of floating variables. Okay. So how should I prove it? And we'll prove it by simple double counting. And before I tell you the proof, any guesses as to how one should do this? Right, exactly, right. Because what does it mean to say it's a set is dangerous, right? It means that row has greater than t non-zero, t ones, okay? And similarly, row has greater than t ones and so on. Okay, but what is the sum of all the number of sets here? Of all the, if I sum up all the ones in this matrix, what is the total? So the total is at most something. What is the at most something? T times n, right? So sum of all entries is less than n times t. Okay, but each row here has more than t ones, right? Is less than or equal to. This is important. Okay, so the number of such rows must be less than n. Okay, so that's the proof when f is everything. More generally, if f was a subset, you can still use the same argument. Okay, and still each row restricted to the green columns has more than t ones. That's the definition of a dangerous set. And now if I only sum up the columns corresponding to the dangerous, to the floating variables, so the sum should be at most t times the size of f, right? Should be at most t times the size of f. Okay, and since each row has more than t ones, the number of rows should be less than the number of floating variables. Okay, so this is simple double counting. And so this is an invariant, meaning it's true for every set of floating variables, and we'll maintain this throughout. Okay. So let me now describe the algorithm. So at each stage you have a vector x which is minus 1 1 to the n, and we look at phase r, and we'll also maintain another invariant. Okay, and initially x0 is all zeros. Okay, the second invariant we'll maintain is that each dangerous set is as balanced as possible. How balanced can it be? Well, the sum could be 0, right? And that is exactly what we'll claim. So summation in each phase if I look at the floating variables f, okay, and any particular dangerous set, and I sum up only those entries in S corresponding to floating variables, I want the sum to be exactly 0. Okay. So, in other words, I have x1 up till x2 up till xn written here. Okay. This is what my candidate solution or candidate coloring is, and the claim is that if I sum up the entries here, well, let me use red. This sum should be 0. Okay. And similarly for the second dangerous set and so on. Okay. So, let us first make sure that this set of constraints is meaningful. Okay. I mean, it is not infeasible or anything. There exists at least one vector x which satisfies this. Well, there always exists a vector x which is the all zeros vector. Right. But I want to say, in fact, there exist more solutions than just the all zeros vector. Okay. And that will be the last claim which we will use throughout. So, we are in phase R, phase 0 is when you started, and I want to let VR denote all x okay. So, I am going to work in a subset VR. Okay. This is the set of all x whose entries are -1 1, and I am only looking at things which are floating, the others are already fixed. Okay. And I want those vectors x which satisfy these constraints. Okay. For every dangerous set, if I look at the sum of the entries, I should get 0. Okay. And right. So, what is VR at phase 0? Right. So, at the beginning, floating variables is everything, and okay, that's also not trivial, but the claim is that so VR is a subspace, right? Okay. Let's just look at all real valued vectors. Then VR is a subspace, because I'm just imposing some linear equations on the elements of all real valued vectors. Okay. So, this gives me a subspace, and I want to claim that the dimension of VR is greater than or equal to 1. Okay. So, there is always a vector in here which is the all zeros vector, right. But as I said, I want to say that there exists at least one non-zero vector in this set VR. And if the dimension is at least 1, that would certainly imply that there is at least one non-zero vector in here. So, what is a good way to count the dimension of VR? Right. So, I am starting with a space which has size the number of floating variables, and then I am imposing a set of linear constraints, okay, linear equations that your vector must satisfy. And how many constraints am I imposing? Each dangerous set gives me a constraint that the vector must satisfy. Okay. So, the total number of constraints I have imposed is at most the number of dangerous sets, right. So, the proof the number of linear equations to be satisfied, the number of linear equations to be satisfied is at most the number of dangerous sets, right? Because each dangerous set gives me a constraint and only that. Number of dangerous sets, and the number of dangerous sets we said is at most the size of f. Okay, it's strictly less than the size of f. Okay, but the total dimension of the space you're working in is the size of f. Okay, that is R to the f. So you started out with the space of dimension size of f, and you impose less than size of f constraints. So the dimension is at least 1. Okay, does that make sense? Please stop me at any point if anything is not clear. Okay, and I'm assuming some familiarity with linear algebra here, just that if you impose linear equations, you get a vector space, and the dimension of any space is at least the dimension of the ambient space minus the number of constraints you're imposing. Okay, these are the only simple facts we'll need about linear algebra. Okay. So what have we shown here? We've shown that this space VR is non-empty. It has at least dimension 1. Okay. So with these tools, we are now ready to describe the algorithm. I'll describe the algorithm by drawing a figure. You can make it formal, but I don't think it gives any more intuition than the figure. So let's say this is the n-dimensional cube. You know, all vectors whose coordinates lie between -1, 1 and to the n. So this is a 3-dimensional cube here, and initially we're starting out at 0. Right? This is the origin, and where does V0 lie? V0 is some subspace. We don't know what it is, but it is non-empty. Right? So it looks, you know, maybe something like this. Okay, this is V0, let's say. All we know about it is that it's non-empty. And if it is non-empty, that means it has a line in it. Okay? So there exists some line. Okay? So the algorithm is very simple. You know the subspace is non-empty, so there exists at least one line in it, and let's pick this line and just go along it till the very end. Any direction you want, you know, downwards, upwards, just go along it in one direction until you hit the boundary of the cube. So you start from here and you move along this line. I'm drawing it squiggly here because I just want to show it to you, but it's actually just moving along the line until you hit the boundary. Okay, that's it. So what does it mean to hit the boundary of the cube? Okay. It means you set a new variable, you fixed at least one of the variables to be 1 or -1. Something which was not 1 or -1 has been fixed to be 1 or -1 when you moved to the faces of the cube, and that's progress for us. Right? We started off with something which was in the inside of the cube. At the end, we want something which lies on, which is one of the vertices of the cube, and we're getting closer to that goal. Right? So that's the algorithm. So you pick a line in this subspace VR, just move along it. Okay, and set xr plus 1 equals point hit. So for our case, x0 was here. You move along the line, and x1 will be here. Okay, so that's your x1 now. And we need to change the set of floating variables now, because once you hit 1 or minus 1, we are never going to change that variable. So that variable will be frozen for us. So fr plus 1 is minus okay. So you have your original collection of floating variables, and you fix some of the things to 1 or minus 1. So just remove them from your set of floating variables. This gives your fr plus 1, and then you repeat the process. Okay, and you go up again. You know that Vr plus 1 is non-empty again by the same process, same argument, and you repeat. Right, and at each step, you are decreasing the size of the number of floating variables by at least 1. Okay, so you should eventually decrease it to empty set. And what happens when the set of floating variables is empty? Everything else has been fixed to 1 or minus 1, right? So output xr whenever whenever you hit whenever the set of floating variables becomes empty, just output that vector you have. Output the vector you have. Okay, so that's the algorithm. Right. Well, that's very good in terms of the algorithm, but we haven't proven anything about what it does to the discrepancy. Right, and but that's not too hard. It's actually very elegant. Let me erase this part. So I want to claim that the discrepancy of the final vector output by this algorithm is at most 2 times t. Why? Well, I erased it, but we had this invariant that for every dangerous set, so for every dangerous set, if I look at the sum of the x's in the floating variables in the set, I get 0, right? That was an invariant that we maintained throughout the execution of this algorithm. We started out with this condition, and at every step of the way, we maintain this condition. Okay. So now remember that a set is dangerous if its intersection with the set of floating variables has size more than t. Now, if a set becomes not dangerous at any point, can it become dangerous again? No, right? because I'm only removing things from this green set here, right? And once the size falls below t, it can never go up above t. Okay? So the proof is very simple. If a set becomes non-dangerous, it stays so. Okay? So once it falls below being dangerous, it stays so. It never gets back dangerous again. Now what happens at the first moment, right at the time it became non-dangerous? Okay? Well, we said that this condition holds, right? So if at the first time the set is become non-dangerous, let's say that happens at phase r, okay, then okay. So the sum was 0, right? Sum of every dangerous set is 0, and the first time it became non-dangerous, the sum is still 0, right? Just before that it was 0, so it stays 0 even now. And so it was 0 now, and what happens in subsequent runs? Well, right, to tell you the truth, I have no control over what happens in the subsequent rounds, but I do know that in subsequent rounds, the size of this intersection is going to be at most t, right? That's the definition of being dangerous. So whatever I do next, I'm only affecting t elements in your sum, right? So how much can I change the sum to be? So I know that the sum of everything here, let's say example, is sum equals 0, and I'm fixing everything. Let's call the fixed ones x, okay. But there are some t elements here which I have no control over. They are still floating. They can go from 1 to -1 or -1 to 1 and so on. For example, I could start out with 0.9 and then maybe eventually I'll output -1 here. I don't know. But I'm only changing t elements here, and each element changes by at most 2. Right? The worst case scenario is you go from 0.9999 to -1. Right? I can't do anything else. So the total change for this sum is going to be at most 2 times t. Right? There are t elements that I'm changing. I'm not changing anything else, and each element changes by at most 2. Right? Therefore, right? So in particular, if I write it properly, I get I belongs to S is less than or equal to 2t. Right? So because I start out with 0, and there are t things that I'm changing, and each changes by at most 2 or -2. So the net sum is going to be at most 2 times t, which is what we wanted. Okay? And you can also squeeze in a -1 here, because if it were 1 here, you're not going to go to -1, you'll just stay at 1. You can only go from 0.9999 to -1. Right? So the net change is actually strictly less than 2. So the sum is less than 2t, and since the sum is actually an integer, it has to be less than or equal to 2t minus 1. Okay. So that's the proof. So as you can see, it's somewhat surprising and it's very elegant. The only thing we used here was that the dimension of this space is greater than or equal to 1. Okay. So right. And in the next half of the talk, I'll sketch a slight generalization of this proof to a more powerful result, okay, which will be the partial coloring lemma. And so there again we'll do a similar walk, but it will be more complicated, slightly more complicated, a tweak on this. Okay. So any questions so far? Okay, all right. So that was the Backfill theorem, and let me state some open questions about it, which are very, very interesting. And one of the main open problems here so in the same paper that they introduced this method, which gave this 2t minus 1 bound, and as I said, we haven't obtained very strong improvements besides this minus 3 and minus 4 really, but so there's a conjecture by Beck and Fiala from 81. Okay. So the conjecture is that the bound should actually be square root of t and not 2t. Okay. And if you can get any improvement where maybe it's not square root of t, but t to the 1 minus epsilon, t to the 0.999, or even for the time being get any small constant here, that would be interesting too. Yeah. So lower bound is square root of t. Okay, so there's a lower bound of square root of t, and nothing beyond that. Okay. So this is if you want a bound which is independent of n. And in my view, this is I think one of the main open questions in combinatorial discrepancy. There are many other questions, but this is the one I like the most. And there are better bounds known than 2t minus 1 if you allow dependence on the size of the universe. At the beginning I said, the most notable thing here is that it does not depend on the size of the universe, right? It's independent of n. And there's the result of Srinivasan. Well, I forgot the year, but look it up. So in 97, we showed that the discrepancy equals so it's square root of t times log n. Okay. So if you're willing to introduce some dependence on n, then you can beat the linear dependence on t. But you can't get the best of both worlds. And the best result known currently is I actually practiced the spelling a few times, if you care about it. So the discrepancy is okay. So here the log n is actually inside the square root. I mean, this might seem like a small improvement, but conceptually there's a huge difference between the two methods, and it remains a big bottleneck to go beyond this, okay, even for very special set systems. So there are other interesting cases which seem somewhat easier, but no one has been in progress. So if you want to know more about any of these open questions, just send me an email, or you can look up the two books that I mentioned at the beginning. Okay. So that's a bit about the history of the problem. Now, let me briefly state, since we have 15 minutes before the break, the next result that I'm going to talk about, which will build on this in some sense. So this will be the so the history of the result I'm going to talk about is a little confusing. So it's proven by Spencer in 86, I think, 85. Okay, but there was also an independent proof by Glushkin. So let me call it Spencer 85, Glushkin 88, I think. So Spencer called it the 6 standard deviations. Suffice. He called it the 6 standard deviation suffice theorem. And so here you have a set system. Let's say it's of size exactly n, where n is also the size of the universe. So you have n sets in a universe of size n. So in matrix terms, you have a square matrix now. Right? You have S1 up till Sn, and you have 1, 2, 3 up till n. Right? And the question is, how bad can the discrepancy of such a set system be? Okay. And if I take a random coloring like before, so a random coloring has discrepancy square root of n times log n, right? So as we saw before, if I take a random coloring, the discrepancy will be O of square root of n times square root of log n. Okay. But Spencer actually showed that the discrepancy is less than or equal to 6 times square root of n. Okay. And it's called the 6 standard deviation suffice theorem because there is a 6 here, as you can guess, and square root n is actually the standard deviation of a single random coloring. Okay. And this is very surprising because so it does not, I mean, this log n might seem like not that big an improvement, but the big deal here is that it beats random coloring. Okay. So if you recall the random argument, the argument we had for bounding the discrepancy for random colorings, we had various events and we took the union bound across the different events. And you cannot do that if you want such a bound. Yeah. Right. Actually, if you have m sets, if size of S is m, then you can show a bound of so basically you get a bound which is square root of n times log of m over n. So if m is n, then this is a constant. Okay? And if m is much bigger, then you don't get anything. Okay? So this is the more general bound. But you can kind of reduce from this case to this case. Maybe without the 6, but with an O off term there. So notable thing about Spencer's result is that it beats union bound. And this is not just an artifact of the simple argument we use for union bound. In fact, if you take a random coloring, there exists such systems where with high probability the discrepancy is this high. Okay? So there exists systems where random has discrepancy theta of square root n log n. Okay? So we need a completely different proof technique besides random. And the proof technique, so Spencer's original argument was different. It built on what's called the partial coloring lemma, which I'll talk about in the second half. And okay, and so that's what we'll see, but we won't go through, I won't discuss his proof, but I'll discuss a more recent proof of this result due to myself and Shahar Lovett. And let me, well, we'll talk about the proof in the second half, but there's one interesting thing that our new proof has, which the old proof didn't. I mean, it's a different proof, that's one thing. But more importantly, being a computer scientist, it also gives something which is constructive. Okay? So Spencer showed that there exists a coloring which has discrepancy 6 times square root of n. Okay? But he gave no algorithm for finding such a coloring. If you look at Backfill's proof, what I've written here is an algorithm. You can code it up in C or any other language you want and get a coloring chi which satisfies the discrepancy bound that you're claiming. Okay? But Spencer's proof was not algorithmic. It used the pigeonhole principle, and pigeonhole principle, whenever you're using it, it's tough to make it algorithmic. Okay? And the new proof, as we'll see, is actually constructive. So it will be an algorithm very much along the lines of the one we saw here, okay? And it will prove the result. So with that, let me stop, and the second half we'll see the partial coloring lemma. All right. Okay, let's start the second half, and as a reminder, we took a break after I just stated the 6 standard deviation suffice theorem, and now we'll see a proof, and the proof will be less detailed than what we saw before, but the details that we'll skip are not too hard to fill out. And so one thing I have to say is that so Spencer proved this result in 86, and for a long time it was open to find an algorithm to find this coloring, and in fact he also conjectured in late 80s, conjecture. There exists no polynomial time. So he conjectured that there exists no polynomial time algorithm to find a coloring chi such that discrepancy chi of s is O of square root n. Okay, and now, like all good conjectures, this was proven to be false by Nikhil Bansal in 2010. So there does exist an algorithm. A polytime algorithm. Okay, and today we'll see a different proof of this result. And Nichols' algorithm, actually, even though it gives a polynomial time algorithm, it still appeals to the non-constructive proof, but we'll see a different proof which will also give us an algorithm. And the proof, as we'll see, is very similar to the Beck-Fiala result. Okay. So let's recall what we want to show. We have a set system with n sets, and we want a coloring with discrepancy O of root n. So we'll follow what's called the partial coloring method, and this was introduced by Beck in 80. So this is partial coloring. And this is a very beautiful method, and to me, to this day, it seems very surprising that it's very effective, given that the full problem is so hard. And the method is as follows. So what we want is a vector chi in 1 minus 1 to the n, such that for every set in your set system, the summation of the elements is O of root n. Okay, so this is our goal, and Beck suggested, okay, it's too hard to find a 1 minus 1 coloring. Let's try and find something where it is 0. Okay, let's say you're shooting for a bound. Let's call it delta. Delta will change, so that's what you're trying to beat. And he said, okay, let's just find a 1 minus 1 0 coloring. Okay. Well, as stated, this problem is trivial. Why? All zeros. You can just take the all zeros vector as before. Well, so not quite so fast, and here's the twist. You want chi such that this is true, and most importantly, at least half of the chi i's are 1 comma minus 1. Okay, or in other words, so at least half of the coordinates should be non-zero. So I want 1 minus 1 0 coloring where half are non-zero. Okay, so and this we'll see is much easier, and once you solve this problem, it's actually easy to solve this problem. Okay, so let's see the second part, which is, let's say I give you a coloring chi or a method to solve this problem. How can I solve the full coloring problem? Well, the solution is somewhat simple, and I'll only sketch this part. Okay, and the details can be filled out, or you can look up the references I mentioned. And the proof is as follows. So you have 1 through n, you have your sets S1 through Sn. Okay, and so you apply the partial coloring lemma, okay, to find a partial coloring. So you find n over 2 elements. Okay, so these are 1 minus 1 minus 1, let's say, and these are 0. Okay, so this is your first partial coloring. And what do we know when you look at this first partial coloring? The sum of each row is at most square root of n. Okay, so that's what our assumption is. And Beck suggested, well, you solve this problem. So this is chi1. Okay. Now since we know what these guys are, let's just ignore them. For the second part, we are just going to ignore them and repeat the procedure on the things which were colored 0 in the previous round. So we just repeat the process again and find another coloring, chi2. And this will have n over 4 elements. Okay, we started out the partial coloring will have half the size of the universe, and now it's n over 4, and we repeat this process, right? Then we'll have chi3, which is n over 8, and so on. Okay, eventually we'll color everything, but initially we just color half the elements every time. So what does this give us? And the final coloring will be like, you'll take chi1, concatenate with chi2, and so on. Okay, but what's the discrepancy bound you're going to get? So initially we are going to shoot for a bound of square root of n. Okay, and more generally what we'll aim for is square root of n times log of m over n. Okay, so this will be our partial coloring claim, that there exists a coloring where at least half the coordinates are non-zero and the total discrepancy is this much. So the first step m is n, so you get roughly square root of n, and the second step we are going to get square root of, second step we are working over a universe of size n over 2. So you should get a discrepancy of roughly square root of n over 2. Okay. So this is contribution from chi1, and this is from chi2, and what should happen next? You should get a contribution of O of square root of n over 4, right? You went from n over 2, n over 4, and so on. So what do I have here? I have a geometrically decreasing series, right? And so the sum will be dominated by the first term. Right? This is just O of square root of n, okay, which is what we are shooting for, right? So what we want to do now is to just solve this partial coloring problem, and once we have it, we can solve the whole thing. Okay. And for this talk, I'll just simplify and shoot just for this claim, and the general log of m over n is not too hard to go to get once you have this claim. Okay. Right. So to to tell you the new proof, let me rephrase this problem in a geometric language, and the proof will also be a geometric proof. So, okay. So we have all of these constraints here, right? The summation of the xi's of the chi's in each set is at most O of root n, and let's call this parameter delta. We'll set delta to be root n at the end, but initially it helps to have some flexibility about it. Okay. And so if you think of the set system, we have 1 through n, S1, S2 up till Sn. Okay. So let V1 denote the first row. So this is just the indicator vector of the first set. Okay. And V2 is the second row up till Vn. Okay. Now there's a different way of writing down this condition. The sum of the entries in the set S of chi is at most delta. How? Well, I can look at the inner product of Vi with, or let's say Vj, with the vector chi, right? This inner product is just the sum of the entries in the jth set of chi. Okay. So if I want to bound this sum, I might as well just look at this inner product between the vector and the coloring vector chi. Right. So what we want is this inner product to be at most this much for all j. Okay. So these are the constraints we want, and we also want chi to be 1 minus 1 0 to the n. Right. And as before, as we did for the Backfill algorithm, we are going to relax the problem. So instead of looking for 1 minus 1 0 to the n vector, we'll start with, for all j, chi which is in minus 1 1 to the n. Okay. So it can take fractional values, any value between minus 1 and 1. So these are the constraints that we want our vector chi to satisfy, but at the end we also want it to have many coordinates which are 1 or minus 1, right? So if I draw the set of all these vectors chi in n dimensions, what I get is a polytope, right? So I'll have right. So this is the cube minus 1 1 to the n, but now I'm adding these constraints, right? So these would be hyperplanes, so I'm kind of slicing off the cube in n dimensions by cuts. So maybe it will look something like this. You know, this is one cut. Well, okay, so I just cut off one section of the cube, right? And similarly, I could add other cuts. Okay, and this is what our space of all solutions looks like. Okay, So let's call this polytope P. So P is the set of all, if you look at all x such that this is true, then this is the polytope P. Okay. So I just rephrased the question we had in a geometric language. So I want a vector within this polytope P, which has many non-zero coordinates and many which are 1 or minus 1. Okay. So let me just write down that goal. Show that there exists chi in the polytope P such that okay. So I cheated a little bit here when I said when I said this is equivalent to solving this problem. Why? Well, I'm saying that at least half the coordinates are 1 or minus 1. But what about the remaining half? Here I want them to be 0, but here there could be anything in minus 1, 1 to the n. But as it turns out, that does not hurt us. You can do a small tweak to the same to the proof I indicated before, where you restrict on half the coordinates and repeat to get the final bound. So we'll just work towards this goal, and the final reduction does not change too much. Okay. So is everything clear so far? Okay. All right. So now I'm going to describe the algorithm and sketch its proof. So how many of you have seen Gaussian distribution before? Okay. And how many of you have seen tail bounds for Gaussian distributions before? Or like, all right, we'll get to that in a second. So let me draw a bigger picture, and hopefully I can do it. Oh, let's see. So think of this as the cube with a slice. Let me actually draw a bigger picture. Okay. So this is the polytope P from over there, just scaled up. And so let's say here's the origin. Okay. And our goal is to find a point inside this polytope where at least half the coordinates are 1 or minus 1. Okay. And one proxy for having many coordinates which are 1 or minus 1, think of 1 or minus 1 as just being as the coordinates being as large as possible, right? So 1 or minus 2 is not so important. What's important is that they're as large as possible. So one proxy for that is for the L2 norm of the vector to be large. Okay. So norm of x to square is summation xi squared. Okay. So in some sense, vaguely speaking, very vaguely speaking, I want to find a point inside this polytope which is as far away from the origin as possible. And hopefully if it is very far, many of the individual coordinates will also be as large as possible. And half of them will hopefully be integral. So how do I go about finding one? You know, I'm at the origin. I don't know much, so I'll start there. And since I don't know much, I'm just going to do a random walk. So what kind of random walk? I'll pick a random direction in n dimensions. Okay, just pick a random direction, take a tiny step in that direction. So I'll formalize what this random walk is in a little bit, but it will be based on a Gaussian distribution. So I just take a random direction here, take a step in that direction, tiny step, another random direction, take a tiny step, and keep moving like this. I'm just drifting in n-dimensional space. And what happens when you drift? You'll move away from your starting point. Right? And I keep doing that, right, until I hit the boundary of the polytope. Well, now I'm at the boundary of the polytope, and I don't want to cross the polytope because that's infeasible for us. My final point should be inside the polytope, right? And but I still want to keep moving away from the origin. So what should I do? Well, I'm a greedy person, so what I'll do is I'll just keep walking in the space that I can walk in. Right? So I'll just do a random walk, but now I'll constrain myself to lie on the face that I actually hit. So again, we'll formalize this in a second. Yeah. Right, it is. Right. Yeah. So we are just going to walk with the face that we hit, and repeat the process, like, you know. So now this is a different random walk. So let me use a different color until I hit another constraint. So now I was initially walking in the three-dimensional space. I am now walking in a two-dimensional space. Now I have to walk on this line alone. So one-dimensional space. Right? I repeat the process again. So right. Start here, go. Voila. So you repeat this process until you're here. Okay. So that's the algorithm. That is going to be the algorithm. Okay. So let me formalize it now. Okay. So is the geometric picture clear? You just have this polytope. You're walking as much as you can away from the origin. And we'll show that the final point this outputs here, the walk reaches when you stop, is going to satisfy the condition we want with high probability. Okay. And so here's the algorithm. And right, you can do this walk on any polytope, right? And that leads to one of the, that's a good point, that leads to some of the questions that I'll ask at the very end.
Can we de-randomize it at the end?
So as stated, it uses randomness. You know, you need to pick these directions and so on. But there's a de-randomization of this. This was done by Spencer more recently. And before I go further, let me just say that so this we call the edge walk algorithm. edge walk. Well, why is it called edge walk? Technically speaking, you should call the face walk because you're walking as much on the faces, but edge walk sounds cooler. So you're walking on the edges as much as possible. Okay? And so before describing the algorithm, let me just state a few basics of Gaussian distribution. And the main thing that we'll use about the Gaussian distribution is the symmetry. Okay? So here, and when I'm doing this walk, I don't know what my polytope is. But I want the walk to be somehow symmetric. It should not pick any particular direction. And the Gaussian distribution satisfies this property naturally. So you say Gaussian basics, and this is from joint work with Shahar Lovett and myself from 2012. And so this paper is short, and there are also slides, PPT slides from my web page. Okay, so if you want to see more, you can see that. So the first thing is we will look at the n-dimensional Gaussian distribution. So this is an n-dimensional random vector where each coordinate is independently Gaussian with standard deviation 1. Okay, and so we will use three basic facts about the Gaussian distribution. The first and most important for us is the symmetry. Okay, so the Gaussian distribution has a property that if you project it along any direction, you once again get a Gaussian distribution. Okay, so this is fact 1. Let V be a vector with norm of V equals 1. Okay, the L2 norm equals 1. Then if I project it along that direction, so if I have two vectors, like you have your x here and have V here, projecting along that direction corresponds to taking the inner product of the two vectors, right? So what's the projection along here? I want to look at the inner product, right? Then the random variable, then for if x is a random Gaussian vector, then V comma x is again Gaussian with standard deviation 1. Okay, so the mean stays 0 and the standard deviation is 1, and this is true for all directions V. So it's rotationally symmetric. Okay. And this is the main property that we will use. And the second property is called sub-Gaussian tails. So earlier I stated the Chernoff bound, right? So you say if you take sum of n independent plus or minus 1 random variables, the probability that your t standard deviations away decreases exponentially in t squared. Okay, and that's also true for Gaussian distribution. In particular, if x is n01 to the n and v is in Rn, okay. So the probability that the inner product is greater than t times the norm of the vector v is at most e to the minus t squared. Okay, so this is sub-Gaussian tails. So your the density falls off rapidly when you move away from the origin. Okay. All right, we'll need another property, but we'll use it when we get there. And another definition really is the following. So here I just said that you're taking the Gaussian distribution in n-dimensional space, but you can also specialize it for subspaces. Okay, so here the space was all of Rn. Okay, and now let's say I have a subspace V, which sits in Rn, but it has small number of dimensions. It has k dimensions. Okay, then there's also a notion of Gaussian distribution within the subspace. Okay. So n of V is Gaussian distribution standard, Gaussian distribution on subspace V. Okay. So if you want a formal definition, what you do is you pick an orthonormal basis for the distribution V, okay, and choose a Gaussian distribution in that basis. So, or you can think of it as choose an orthonormal basis V1 through Vk for the subspace you're working with, and you just sample G1 times V1 plus G2 times V2 up till Gk times Vk, where each of the i's are independently standard Gaussian random variables. Okay. All right, so these are the three main definitions we need. If you take V to be Rn and the basis to be just a standard unit basis, you require Gaussian distribution. Right? In general, you can define this for any subspace, and there are various ways of generating to coming to the same distribution here because of the rotational symmetry of the Gaussian distribution. Right? So are these definitions clear? Any questions? Okay. So let me now describe the algorithm. And as we saw for the Backfill setting, we'll again move in rounds. Okay. So we start off from the origin, and we're going to set things to be 1 or minus 1 iteratively. And once something gets set to 1 or minus 1, it's never going to change. Okay. And we have our polytope P here. Just for brevity, so there are two kinds of constraints here. So let me write this as so each coordinate should be between 1 or minus 1, and each inner product should be at most this value. So these are the two sets of constraints which define my polytope P. Now let's call the first set of constraints discrepancy constraints. Right, because they are coming from the condition that the set system should have small discrepancy. And let's call these the color constraints. Okay, because they're coming from the condition that each element should eventually be colored with 1 or minus 1. Okay. So these are discrepancy constraints, these are color constraints. So so the algorithm is going to run in phases t equals 0, 1 up till some upper bound p. Okay, and there will be some parameters that we will get to in a little bit. Okay. So the first thing to keep in mind is that I said, you do this random walk until you hit a face, and once you hit a face, you keep walking within that face or that color constraint. But when you're taking these tiny steps, you might not actually hit a face, but overshoot it. Right? So you can like slightly overshoot it. So what you do is just introduce some slack. So think of each face as having some kind of wiggle room. Once you get very close to it, it just gets stuck. Okay. So let's see. Let color T denote the set of all color constraints that are nearly violated by our current solution. So this is set of all xi, xti. So you start with the all zeros vector, okay, and let color T denote set of all I, such that xti is at least 1 minus delta in absolute value. So think of delta as this tiny wiggle room that you have near each boundary. Delta is 1 over poly n, 1 over n squared, 1 over n cubed, anything you want. Okay, and let discrepancy T denote the set of all discrepancy constraints that you are very close to violating. Okay. All j such that the inner product with your current solution xt is very close to the threshold that you don't want to cross. So these two sets of conditions are kind of very tight for us. We don't have much room in these directions. They are very close to being violated, so we do not want to change them at all or affect them at all, right? So let Vt denote.
That delta does not have to be the same delta in both cases.
It can be the same. Just think of it as the same for now. I mean, it doesn't have to be, but it's just something sufficiently small. So it's just small enough so that you don't enter into these discretization issues. Okay. And so I want to walk within this phase, so without changing any of these constraints. So what should my space Vt be? Okay, I don't want to change any of these xi's. Okay, so I should walk in a space where that is 0, where these coordinates are set to 0. Okay, so I have xi equals 0 for all I belonging to color T. Because I can't change these coordinates, they are very close to 1 or minus 1, and once they get close, they are fixed. And these discrepancy things, they are also very close to being violated, so I don't want to change them. So these inner products also I am going to set to 0. Okay, so this is your subspace Vt. So I just wrote down some conditions, some linear equations that my subspace needs to satisfy. So this is similar to what we did for Backfill in the proof of Backfill. We also wrote down some linear equations that our conditions should satisfy, and we were walking within that subspace, right? But in Backfill, we just said that the subspace is non-empty. Pick a direction, and you just move along that direction. But now we have to do something a little different. And here's where the random walk comes in. So you set xt plus 1 to be xt So let's say I'm here. I had to pick a random vector within this subspace Vt, okay, random direction, and you take a tiny step in that direction because I don't want to move too much at any point. So there is some gamma times Yt, where Yt is okay. So I pick a random Gaussian vector from the subspace Vt according to this definition here, all right, and I take a tiny step in that direction. And you can think of gamma as infinitesimally small, okay, as small as you want. It should be smaller than delta, basically. You want it to be sufficiently small so that when I introduce this wiggle room here, something like this, in one single step I do not shoot across. Okay, so that's the only condition. So gamma is step size. Okay, so is the algorithm definition clear? It's, I mean, if it seems like too many parameters, just think of you as drifting until you hit the boundary, and then you drift within the boundary, and so on. Okay. So this is the full algorithm. Okay. All right. I kept it. Now I will basically just sketch the analysis because the calculations are a little more detailed, but they're not too hard to fill out. So let me write it down here. So the claim is that if t is to be some c over gamma squared, okay, this parameter is not important, it depends on how small a step size you're taking. If I'm moving really, really slowly, I need to run the algorithm for really, really long. Okay, that's it. And then with probability greater than or equal to half, xt satisfies the following. So what are all the conditions we want? The first condition is that the final point lies inside my polytope P. I do not want to cross the polytope, right? So xt belongs to the polytope P. And what's the second condition? I want at least half the coordinates to be close to 1 or minus 1, right? So these are the two main conditions, and we're claiming this happens with probability at least a half. In particular, there exists one such xt, right, which is what we want to show for the partial coloring lemma. There exists one, and this algorithm proves there exists one because it is finding one. Okay. So what's the proof idea here? I'll give some intuition for the proof, really. And the intuition is the following. So this figure, I mean, my drawing skills are obviously limited, so we redraw it. So if this is the origin, right? Now how far is the face of a cube from the origin? If I draw the perpendicular from the origin to the cube, how long is it? So this is the face, let's say x1 equals minus 1. So what's the length of this perpendicular? 1, exactly, right? And let's say I'm shooting for maybe not for something like 6 times root n here. Okay, so this is the bound I'm shooting for, right? And I want to look at what's the length of this perpendicular. So this length is 1, and how about this length? I want a lower bound. I want to say this length is at least something. Well, we know that the inner product is at most 6 times root n, right? And the length of this guy, the vector Vj, is at most root n, right? So the length of this perpendicular should be at least 6, okay? Because this is the face. Okay, so this is the constraint. The absolute the inner product is 6 times root n, let's say. That means the distance should be at least 6, right? So I have a distance of 1 here and a distance of at least 6 here. So which is closer to the origin? The cube constraints, the color constraints are much closer to the origin than the discrepancy constraints. Okay, so when you're starting from the origin, you're already pretty close to the color constraints as opposed to the discrepancy constraints. They're very far. So what should happen if I do a random walk? Which should you be more likely to hit? Remember that the walk is spherically symmetric, meaning it moves in the same way in any direction. Okay, so which of these two should you be more likely to hit first? This one, right? You're just walking and doing the same random walk for both of these guys. This is closer, this is farther. So you should hit these guys sooner. Okay. So here's the intuition. Probability of hitting a color constraint. Right, remember this claim that is basically the probability that your t standard deviations away is roughly exponential in minus t squared, right? So the probability that you hit a particular color constraint will turn out to be something like exponential in minus 1 by 4, let's say. Let's ignore this constant because the length of this projection is 1. And by the same argument, the probability of hitting a discrepancy constraint should be exponential in minus 6 squared, right? Because these are at a distance of 6 away. Okay, so this is less than or equal to. So what's the conclusion of these two things? Well, one conclusion is that probability of hitting color constraints is much bigger than probability of hitting discrepancy constraint. Okay, so you're much more likely to hit color constraints than discrepancy constraints. But at the end of the day, let's say you did find a vertex here. When you're no longer able to walk, what should happen? You must have imposed n constraints on yourself, because you started off with n degrees of freedom, and if you're no longer able to continue the algorithm, that means you must have imposed n constraints. And we know that you're more likely to impose color constraints than discrepancy constraints. So the majority should be color constraints. And if you're imposing n constraints and majority are color constraints, then you must have imposed n over 2 color constraints, right? Which is what we want. That's what a partial coloring is for us. Right? And this is vague intuition, but let's write it down. So this implies when at the end you must have n over 2 color constraints. Right? So you're imposing n constraints on yourself, majority are color constraints, so you're likely to have at least n over 2 color constraints. Okay, so this is kind of the basic proof outline, and the actual proof is very much just writing down the probability inequalities to make this work. Okay. So let me just say a few more words and then I'll stop about the proof, not for everything. So the proof involves 3 simple claims. The lemma 1 is that xt belongs to the polytope P with probability 0.9. Okay. So it's just saying that the final vertex your algorithm outputs is going to be in the polytope with probability more than 0.9. Okay. And the proof, which I won't write, is use tail bound. And the reason is the only time, see, whenever you're getting close to the polytope, you're anyway not moving in that direction. So the only time you'll cross the polytope is if it happens in a single step, where you jump by at least delta, right? Because if you are very close to it, you're not moving, you're freezing the direction. So the only time you'll cross it is if in a single step you are on this side and then you jump across at a distance of at least delta. But remember that in each step you're taking a tiny, in each iteration you're taking a tiny step. So if this step size is much smaller than the slack parameter delta, it's not going to happen. So if gamma is much less than delta, then won't cross. Okay. So does this seem believable to you? I mean, you have to take a big step in a single iteration, but you're taking tiny steps, so it's very unlikely for that to happen. And lemma 2, which is kind of important, is that so what is discrepancy T? The discrepancy T is a set of discrepancy constraints that are nearly violated at the very end. Okay, so by definition, this is what discrepancy T is. And I'm saying that the number of discrepancy constraints that are nearly violated is very small. It's 0.01 times n. Okay, and this goes back to the claim here that the probability of satisfying discrepancy constraint, a single discrepancy constraint, is tiny. It's exponential in -6 squared. And if there are n of these things, you can just sum up across the different probabilities, right? It's just a union bound. The proof, once again, I'm not going to go into the details, but probability any single discrepancy constraint is satisfied is less than that any single discrepancy constraint is satisfied is tiny, it's exponential in minus 6 squared. And if there are n constraints, the total number of discrepancy constraints satisfied would be n times this number, which is smaller than 0.01. Okay, does it make sense? Again, I'm not going to the details, but it's it takes a simple tail bound. And the final claim is that and the final claim is that after this many iterations, the space that you're walking in has small dimension, meaning what's another way of saying the same thing? You must have imposed at least n over 2 constraints on yourself. Okay? So you're not walking somewhere here. You're walking in a very low dimensional space. You have satisfied many constraints. Okay? And why is this? Well, it's again just follows from the Gaussian tail bound. Each time step, you're moving some distance away from the origin. You're not just sitting there. You're making some progress. So eventually, you should have moved sufficiently far away from the origin, okay? And hence, you must have satisfied many constraints. Okay. Once again, I'm not going into the details, but does it actually seem believable? You're just making some progress, some non-trivial progress every time, right? Eventually, you must have moved sufficiently far away to satisfy this constraint. And here again, we crucially use the spherical symmetry of the Gaussian distribution. The fact that it does not pick out any single direction is important for us here. All right, so we are basically done. So what happens if I combine all of these lemmas? Okay, so I get that my final vertex is in the polytope with probability 0.9. Okay, and if I combine these two, what should happen for the number of color constraints? Right. So I'm claiming that xt belongs to P, and I was initially walking in a space, I'm walking in a space of dimension n with some number of constraints. Right. There are two kinds of constraints, discrepancy and color, and the discrepancy is small, 0.01 n. So this should be n. Okay. So the final space I'm walking in has dimension less than 0.5 n. I must have imposed at least n over 2 constraints. And out of those, only 0.01 n are coming from discrepancy. other should be coming from here. Okay. So now I can use Markov's inequality again and say that at least this implies let me just put an over here. Okay. So I know that the expectation is roughly n over 2. So I can show that the probability that this it's at least n over 8 is significant. Okay. And now I'm basically done, right? So I have 0.9 here and 0.5 here. So if I combine the two, there should be some intersection between the events, right? So which shows that you might not get 1 over 2 here. Let's say you get 1/4, and you won't get n over 2, but you get n over 8. But these constant factors don't hurt us. You can optimize them and so on. And at some point I did do that. I wrote a MATLAB script to find the right constants, and it's no longer the 6 standard deviation suffice result, but the best constant I got was 13. Okay. But so is the basic proof outline clear? Any questions? So I rushed a little bit here, but believe me that these calculations that I'm hiding, they use some simple properties of the Gaussian distribution. Okay. Simple and nice properties. Okay. Any questions?
How crucial, or where was the crucial step that you used the fact that you have n sets over a universe of size n?
Basically here. So we said that each set is violated, each discrepancy constraint is satisfied with probability exponential minus 6 squared, and if there are n of them, we just summed up across all the sets. So this is actually n times e to the minus 6 squared, which we just wrote 0.01. We can allow bigger than n, but not more than a constant factor. Okay. Right. Any other questions? Yeah.
So, maybe this little strange question. What will break down if you, instead of just picking random world according to the Gaussian distribution, you just choose a random phase and start going in a direction which is like perpendicular to that phase?
So basically the question is, well, let me see if I got it right. So here we're taking these tiny steps like this, right?
Yeah.
And you're saying, okay, why do that? Just pick a random direction,
Yeah,
let's say.
I mean like direction which will minimize distance to some phase. In that picture just going down, for instance.
One step, do it.
Right. So basically like pick a random direction, just go there.
Yeah.
So
Right.
again, you will like, because the discrepancy conditions are far away,
Right.
it will be like low
Right.
probability.
Right. In fact, I do think it works. Okay. But this is easier to analyze. Okay. And one thing to note is that these two are different, which I didn't think. Which I made a mistake of at the very beginning. I thought these two are the same, but there's a subtle difference between the two. So doing a Gaussian, taking this tiny random Gaussian steps is kind of like Brownian motion if you're familiar with it. So you're doing Brownian motion until you hit the boundary. That is very different from taking a random direction and going on it until you hit the boundary. Okay. For example, if you take a thin cylinder, the behavior will be different.
But it's not. It's different, but not too much now.
Right. It's different, but for us it should not be different, I think.
Because intuitively it's,
Yeah.
it's different, but not
Right. Yeah. Right. And I think it should work even with this, but the analysis here is simpler. Basically. Yeah. Any other questions? Okay. So I originally planned to do something else, this application to rounding algorithms, but I'll skip it. But let me just say a few words about it and why this should be interesting for computer scientists. Okay, let me just finish with that. And I also want to lead up to some, I already mentioned some open questions, this Backfill theorem and so on, but there are also some other ones which seem like we have much, we are close by. You know? Maybe we can do it with a little bit more work than at least using these techniques. Okay? So let me state the full partial coloring lemma. So far, you know, we originally started off with this set system. We looked at the polytope P defined by this vectors V1 through Vm, and then we had this threshold delta and did all of these calculations. But if you think about it, we never used the fact that the vectors Vi's that we are looking at were coming from sets. We just used the fact that the norm was small. Okay, and then this threshold delta only appeared because of this. You know, we just summed across all of these different sets. Okay, so you can easily generalize this proof to show the following claim. Let V1 through Vm be vectors in Rn, and lambda 1 to lambda m So I have m vectors v1 through vm, and I have m scalars delta 1 up till delta m. Okay. Then there exists which is in minus 1 1 to the n, okay, such that at least half the coordinates are 1 or minus 1. Okay, just as before, we are getting a partial coloring. Okay, and so originally we said that each discrepancy constraint is violated by at most this parameter delta, which was root n for us. Okay. So now more generally, you'll have the claim that for every j in M, the inner product Vj comma x is less than or equal to lambda j plus okay, as long as, so I don't want to just put a blanket bound to square root n for every set. Some sets are more special than the others, even if people say no. So how do I enforce that? The condition is that all I cared about here was that some of the okay. So if you translate it immediately, what you get is okay. So as long as this potential function, the scalars, oh, wait, this should be norm of Vj. So you have to scale up by the norm of Vj, because that's how many standard deviations you are far away from. As long as you have control on the total number of standard deviations, you get a partial coloring. Okay. So this is kind of a generalization of the claim over there, right? And I mean, this result is fine, but I think the main the power comes from this partial coloring lemma, because using this you can prove a lot of results. For example, the arithmetic progressions bound I mentioned at the beginning builds on this. So you had to be more careful about choosing the lambda j's appropriately. So I also mentioned a bound of square root t times log n for the Beck-Fiala setting, and that also comes from here. In fact, it's very simple to get it. You just have to choose the lambda j's appropriately. So this gives you a lot of flexibility on how to choose the lambda j's and how do you play them together against one another. And so examples. Discrepancy of arithmetic progressions, discrepancy of rectangles. So I haven't defined rectangles, but it's a very natural definition where you're trying to fool sets which correspond to rectangles in low dimensions. And there are many other results like half spaces and so on. Okay, so there are many applications of it. And so the proof I said here actually gives you a constructive version of this partial coloring lemma. Okay, so you can find an x which satisfies these conditions. And the open question, one of the open questions is to make all of these applications constructive. Okay, so it's not so easy to, I mean, in many cases it's easy, but for example, for arithmetic progressions, you have to do some very careful arithmetic to go from here to the final bound of square root of n to the 1/4. Okay, so let me just state that. So there are all of these other applications of the classical partial coloring lemma, which was introduced by Beck and many other people. And one natural direction to explore is to use the constructive partial coloring lemma to make all of these applications constructive. Okay, and some of those I think will be immediate, some of these may not be so, but they should be reachable at least. Okay, so that's one nice, I think, not too hard, or at least that would be my guess, direction for future projects. Okay, and a more philosophical question, I think, is explore properties of edge walk. So the partial coloring statement I said here, I mean, this algorithm could be useful in other algorithm, other contexts where you're interested in rounding. Okay, so what do I mean by rounding? So you have a fractional solution, a vector in -1, 1n, which satisfies some linear constraints. But what you really care about at the end is an integral solution. Okay, this is called linear programming rounding or rounding in general, and that's exactly what we did here. Right? We started off with the all zeros vector, which is a fractional solution, and we went to an integral or almost integral solution. Okay, and this is a very powerful technique and powerful and often used technique, rounding, in computer science and algorithm design, and it would be nice to explore if this could be useful in other places. And one kind of broad question is to study what properties does this walk have. So you can define the edge walk for any polytope. So you have some polytope. It doesn't have to be this discrepancy constraints and cube constraints anymore, but it's just any polytope. And you start from the origin, take a random walk until you hit here, and so on. So what you get at the very end is a distribution on the vertices of the polytope. Okay. So you're going to reach a vertex with some probability p and so on. So are there does this distribution have any nice properties? Okay, so that's one thing to explore. For example, so if you start with the simplex, okay, so this is kind of like the triangle in 2 dimensions, in 3 dimensions, sorry. So if you start with the simplex and do this algorithm, what distribution do you get? Well, any guesses? So what's the probability that you reach here, or here? The answer is easy to figure out, is probability is proportional to these lengths. Okay, so if you start very close to this vertex, you should be more likely to hit here, right, and so on. Then in fact, it will just be the probability of reaching here is exactly this length, and so on. All right. So these are some questions. Example for simplex, the distribution proportional to lengths. But for other polytopes, I don't know. What happens for the cube even? That's another exercise. You can figure out without much difficulty, but it's a nice exercise nevertheless. So I have the cube, but I'm not starting at the origin. I start somewhere here. What should the probabilities be of reaching this vertex, this vertex, this vertex, this vertex? More complicated polytopes, I have no idea. And it will be nice to have some meta properties for these things. Okay, and they might have applications to other algorithms. All right. So let me stop there. And if you have any questions, just unfortunately, I'm not away for the next few weeks. But you can email me, or you can find the paper and the slides online.